Good morning or afternoon, girls and boys. Today we're going to talk about Lesson 8, Equal and Equivalent. And you can see right off the start that equal and equivalent are very closely related. As a matter of fact, the word equal is in the word equivalent. So you know that they're very, very similar. So we're going to use diagrams today to figure out expressions that are equivalent to each other and sometimes expressions that are just equal to each other. Learning targets for today, I can explain what it means for two expressions to be equivalent. I can use a take diagram to figure out when two expressions are equal, and I can use what I know about operations to decide whether two expressions are equivalent. Let's just briefly talk about those and what they actually mean. We've already done a bit of this because I can explain what it means for two expressions to be equivalent. Notice this. If we have an expression, 3 plus 2, on one side, we know that that is equal to 4 plus 1. So that's an example of two expressions that are equivalent. And there are obviously an infinite amount of those that we could come up with. I can use a tape diagram to figure out when two expressions are equal. We did a bit of this when we worked with ratios and proportions, and we'll continue to do that. So we can use a tape diagram to see if they're equal. And I can use what I know about operations to decide whether two expressions are equivalent. And again, something we've talked about several times. We've talked about the fact that multiplying by a half is the same as dividing by 2. So notice that in these two expressions that I'm creating here, 1/2 times 10, well, that's equal to 5. And 10 divided by 2, also equal to 5. Obviously, these operations are the same. Multiplying by a half mathematically is exactly the same as dividing by 2. So you've had a bit of exposure to this already. So we start our lesson with an algebra talk. And we're going to solve each equation by seeing the structure. And really, what we're learning is a language, boys and girls. Mathematics is a language, and algebra specifically is a part of that, language. And we have to learn the symbols, what the symbols mean, and what certain things mean. And really, it sometimes looks a lot more complicated than it is. I know you can do the first two. There's no question at all. So go ahead and solve those in your own way, whichever way you want to use. And then we will do this third one and fourth one as well. You can go ahead and give those a try, boys and girls. But again, those are a little bit trickier just because of they look more complex. And we'll talk about those as well. So I encourage you to pause the video, do as many of those 4 problems mentally as you can, and then we're going to talk about them. So you can go ahead and pause, do the 4 problems, write down the answers in your math notebooks or your remote folders, and then we will chat about them momentarily. All right, so hopefully you paused the video and we solved these. So obviously the first one, that's right. X is equal to 5. Now we can know that because we know our math facts and because, of course, we can see that when we add 5 to 3, it's equal to 8. A lot of different ways. As a matter of fact, you did these problems similar to the first two when you were little tiny tots in 2nd or 3rd grade, except instead of an X, they used a box, an empty box. Now notice what we could have done in this situation is we could have simply subtracted 3 from both sides of the equation. Because as long as you do the same thing to both sides of the equation, you're still keeping that equation in balance. And therefore, in this particular case, you'd end up with X on the left side, and you'd end up with 5 on the right side. So X is equal to 5. So there's a more formal approach for this other than a guess and check strategy or using basic math facts as well. And the next one, I'm quite confident that you all came up with that X is equal to 2. The third one, a little trickier because we have to remember what x squared means. Well, what does x squared mean? X squared simply means x times x. And x, in this particular case, we're looking for a number, when multiplied by itself equals 49. Well, obviously, after some thought, we can say, it must be 7, because 7 times 7 is indeed 49. So that's one way you could approach it. And the last one, 1/3 times x is equal to 3. Well, remember when we talked about the half when we were up here? We talked about the half times 10 is equal to 5, is the same as 10 divided by 2. Same thing. So here, we can set this up, and we can say, okay, 1/3 times some number, and then we're using x instead of a question mark or something of that nature, equals, or empty box, equals 6. So some number multiplied by 1/3 equals 6. It's the same as saying some number when divided by 3 equals 6. Well, once we phrase it that way, I think most of you already know that x must be equal to 18. Now also watch this. This coefficient on this variable is attached through multiplication. I know that because it's right next to it. There's no space between it, and there's no symbol between it. So I can actually detach that through an opposite operation. So I can actually get rid of this 1/3 times x by dividing by 1/3. Well, dividing by 1/3 is the same as multiplying by 3. All right, it's the same thing mathematically. So I could actually do this. You remember when we were dividing by fractions, by the end of the unit, we really weren't dividing by fractions. We were multiplying by the reciprocal. Well, the reciprocal of 1/3, of course, is simply 3/1, which means you would do the same exact thing to the other side. This all factors out to just be 1x, or x. And of course, this is 6 times 3, which is 18. So that's another way to do it. Now, don't be jealous of this 8, boys and girls. It looks a little bit like a sideways infinity sign, but it is 18. All right, the next section here, let me get rid of this writing. The next section here, we're going to use diagrams to show that expressions are equivalent. So in the start here, we have a diagram of x plus 2. This is the x plus 2 diagram, and this is the 3x diagram. And it says these diagrams reflect x plus 2 and 3 times x, or 3x, when x is 4. And indeed, we could check to make sure they did that correctly. There's 1, 2, 3, 4. Sure. And there's 3 sections of 4. And of course, this is a model of 6, and this is a model of 12. Okay, fair enough. In the next section, they're asking us to create a diagram. And we're going to do the first one together, and then I'll pause the video again, and you guys can go ahead and do the rest of them in your math notebook or your remote folder, and then we'll check our work together. So draw a diagram of x plus 2 and a separate diagram of 3x when x is equal to 3. Well, x is going to be equal to 3 this time, so my first diagram, I need an x worth 3, and that's the x, and then I need 2 more. And of course, that's a model of 5. And when they say they wanted us to line it up, they meant they wanted us to start it at the same place. So I'm going to start the next one with 3x down here. And remember, x is equal to 3, so I need 3 sections of x, and each time the x is going to be worth 3. So there's that diagram. And the reason they wanted us to do this in this manner is we can see from the diagram, x plus 2, of course, is equal to 7. So this part's equal to 7. Thanks, Bets. And 3 times 3, or 3 plus 3 plus 3, this is equal to 9. So they wanted us to line it up so that we could see inherently that those are not equivalent. They're not equal. Okay, so I'd like you, let me erase that. You know, boys and girls, when I first started teaching, I had chalkboards in my room. I was down in a room Mrs. Bystrick uses, and they were all chalkboards. And I tended to wear black or blue pants back then, and the chalk would just I'd be full chalk by the end of the day. Okay, so I'd like you guys to give 2, 3, and 4 a try. Okay, and again, you can do this with somebody by doing a Google Hangout. I would encourage you to do that as often as you can for these types of problems. And then if you're alone, then you're really doing it with me. So just pause the video, do the best you can, and then we're gonna do each of these. And then as is typical, I'm going to assign. Actually, in this case, we're going to do this together, the identifying equivalent expressions. And then I'm going to have you, as always, read through the lesson summary as carefully as you can. And then we are going to do let's see, this time the practice problems. Let's just do the first 3. This time we're going to do the first 3 practice problems. I'm going to make a note of that. Lesson 8. Practice problems 1 through 3, which you'll do in your math notebooks or remote folder. And then, of course, the exit slip that you're going to send to me. Make sure you're keeping your math notebook or math folder so that it's all together for when we finally go back to school. So I'm going to pause the video now, and then we'll come back and we'll finish off the problems that we need to do. So right now, you're going to be working on 2, 3, and 4, drawing those diagrams. Give those a try. Okay, so hopefully you've had time to try to draw those diagrams. I did. I apologize for the penmanship, boys and girls. I promise I will get better. So draw a diagram of x plus 2 and a separate diagram of 3x when x is equal to 2. So here's my x is equal to 2. Here's my 2. And of course, that value is 4. And the 3x, and of course, x is equal to 2. So 2, 2, and 2. So obviously, these are not equivalent. And this one adds up to 6. This one, of course, adds up to 4. Next one, draw a diagram of x plus 2 and a separate diagram of 3x when x is equal to 1. Well, this time x is equal to 1. So here's my x is equal to 1. And here I have the 2, a total of 3. And we notice this, in fact, is equal because this x and this x and this x are each 1. So they're both of these expressions are worth 3 when x is equal to 1. And the last one, draw a diagram of x plus 2 and a separate diagram of 3x when x is equal to 0. Well, if x is equal to 0, doesn't have anything, so there's nothing there. It's a total value of 2. And of course, we know that 3 times 0 is going to be 0, so there's nothing for that. Nothing for that at all. So in our diagram. So I'm going to get rid of that. That's weird.